Good day, everyone. Today, I'll be talking about some topics about aerodynamics. But before I do that, let me introduce myself first. So, I'm Mark Rebaja, a third year student from Philippine State College of Aeronautics, studying Bachelor of Science in Air Transportation. In this video, we'll break down the physics behind incompressible flow and in the speed of sound and explore their foundation and how these concepts are applied. So the concept will be incompressible flow, regime of aerodynamics, and lastly, the speed of sounds and the Mach number. So let's talk about the incompressible flow. Incompressible flow refers to a type of flow where the density remains constant throughout the motion. This means that regardless of changes in pressure or other conditions, the fluid does not experience significant variations in density. So what does that mean? It means that in change, whether we have changes in pressure, we have constant density. So therefore, we neglect density. So what is incompressible flow? These flows are measured in less than 100 meter per second. They are low speed and subsonic. So the Mach number for this to know that its incompressible flow is Mach 0.3. So we'll talk about the law of continuity, Euler's equation, and lastly, the Bernoulli's principle. So law of continuity. Mass can't be created nor destroyed. Now we'll have mass flow rate. M dot sub 1 is equals to rho sub 1 times the area sub 1 times the initial velocity. Its SI unit is kilogram per second or slugs per second. Now we know that mass can't be created nor destroyed, then therefore we have M dot sub 1 is equals to M dot sub 2. Then we will have the conservation of mass, which is rho sub 1 times the area sub 1 times the initial velocity is equal to rho sub 2 times the area sub 2 times the final velocity. Now, how did the Euler's equation form? So, we know we have two pressure, force rather. So we have two forces. One is in terms of second law of Newton, which is the law of acceleration, and the other one is in terms of pressure. So we know that pressure is equals to force over mass. Force over mass. If we find force in terms of pressure, we will have force is equals to pressure times the area. Oh, sorry. I think I was force is equals to pressure times the area. Um, so we have the area right here in this side, and the area, we know that the area is side squared, so we'll have dz times dy or dy times dz. Next is the pressure, the pressure in the right side, here in the right side. So we have pressure plus the change in pressure over dx times dx. So what is this dp? This dp is the change in pressure in the lateral side, and we have the pressure in the left side. So p sub 2 is equals to p sub 1, and like I've said earlier, the area is dy times dz. So if we get the summation of forces for both sides of pressure, we'll have p times dy dz minus p plus change in pressure over dx times the area. So why is this negative? Sign convention. When the pressure is going to the left, it's negative. When the pressure is going to the right, it is positive. When the pressure is going upward, it is positive. Then downward, it is negative. So then we'll sum it up. Then we'll arrive at this equation where the force is equals to negative dp over dx times dx dy and dz. So that is in terms of pressure. Now let's go to in terms of the law of acceleration. Now we all know that force is equals to mass times acceleration, and mass is equals to rho times the volume. So volume is length times width times height. So well, dx times dy times dz. So we'll have mass is equals to rho dx dy and dz. And we all know that the acceleration is the change in velocity over the change of time. Then uh, we'll times the numerator, and we'll multiply the numerator and denominator by dx. Then we'll arrange it. Then we will arrive at the acceleration is equals to change in velocity over dx times the velocity. We know that velocity is equals to distance over time, and we will arrive at this equation. Now we have two forces in terms of law of acceleration and in terms of pressure. We will equate it to each other. Then we will arrive at the Euler's equation, where change in pressure is equals to negative rho times the velocity times the change in velocity. So this is the Euler's equation, and this is the Bernoulli's equation. So how did we arrive in Bernoulli's equation in terms of Euler equation? Simple. We'll integrate it both sides. So integrate both sides. So negative rho is constant, and the integration of dp and integration of v dv. So upper and lower limit, p sub 2 minus p sub 1 times the equal to negative rho v sub 2 squared over 2 minus v sub 1 squared over 2. Then we will arrange the equation. Then we will arrive at this equation called the Bernoulli's equation. So application of the incompressible flow is at aerodynamics at low speed. So aside from that, we have also in terms of aerodynamics and water flow. It also includes marine engineering for buoyancy, and in sometimes medical equipment. And the more important to us as a aeronautical student is the wind tunnels. So these devices measure the flow rate of fluid through a pipe by using the principle of incompressible flow, as the fluid flows through a concentric section of the pipe or the venturi. Its velocity increases and its pressure decreases, as stated by the Bernoulli's principle. So now let's talk about the regime of aerodynamics. We have subsonic, Mach number is less than 1. Sonic, where the Mach number is equals to 1, or sonic is also a term for this equal to speed of sound. Supersonic is greater than Mach 1, and transonic is 0.8 to 1.2. So transonic is the transition between the subsonic and the supersonic, while the hypersonic is anything that is greater times 5 the speed of sound. So subsonic flow is primarily incompressible with neglect in density. So incompressible flow, like I've said earlier, that it is Mach number is equals to 0.3. Anything that is more than 0.3 is considered as compressible flow, where we don't neglect density. So sonic is airflow is equal to the speed of sound, and supersonic flow is compressible, air density varying significant across shock waves. And the transonic is formation of shock waves usually over the wings or other surface, leading to changes in lift and drag, while the hypersonic is intense in aerodynamics, heating due to friction and compression of air, leading to high temperature. So next, we have the speed of sound. We have ahead of sound and behind the wave. So let's call it point 1 and point 2. And in the middle, we have the motionless sound wave. So we have here the conservation of mass, and here is point 1 is equivalent to point 2. We'll change the velocity to speed of sound, since the speed of sound is also a velocity. So in this equation, we'll eliminate the area. So how did we get the rho sub 2? It's here, and the velocity sub 2, it's here. A plus the change in dA, or dA rather. Then we will, once we eliminate the area, we'll arrive at this equation, FOIL method, simplify, then the speed of sound is equals to negative rho times dA over dP. So Euler's equation, A is also velocity. So we'll change the velocity to negative rho times A dA. Then simplify, dA is equals to negative dP over P rho sub A. Then we'll substitute this equation to this equation, and we'll arrive with this equation and simplify. Then we will get the speed of sound, where the speed of sound is equals to the square root of the change in pressure and the change of density. It is isentropic, meaning there is no heat added. So P sub 1 over rho is constant. So constant, and then we'll arrange it. Then we will get the dP over the change in pressure over change in density is equals to P sub 1 over rho raised to K times the gamma, or rather gamma times the density raised to gamma minus 1. Then simplifying, we will get the gamma times the pressure over density. So using the equation of state, we know that the pressure over density is equals to the specific gas constant times the temperature. So simplify, and then we will get the speed of sound is equals to the square root of gamma of air times the specific gas constant times the temperature. So the speed of sound is given, like I said earlier, is that A is equals to change in dP over d rho. Then for the equation of state, we'll get the speed of sound is equals to square root of gamma times dr times t. So speed of sound barriers travel in the air and considered as obstruction. That's why we considered this speed of sound. So lastly, the Mach number. The Mach number is a dimensionless quantity that represents the ratio of the speed of sound and the air and the velocity. So it is the ratio of velocity over the speed of sound, and the speed of sound is, we know that the speed of sound is equal to the square root of gamma times r times t. So the gamma of air is 1.4. So application, aerospace engineering and aeronautical engineering. So design of aircraft and spacecraft. Engineers use the speed of sound to design and analyze aircraft and spacecraft, especially those operating near or beyond transonic speed. Understanding how airflow behaves at different Mach numbers is crucial for optimizing performance, stability, and safety. So we'll go to with the sample problems. Consider an airplane flying with a velocity of 60 meters per second at a standard altitude of 3 km. At the point on the wing, the airflow velocity is 70 meters per second. Calculate the pressure at this point. Assume incompressible flow. So you have a given of the initial velocity of 60 meters per second and the height is 3 kilometers. Converted to meters, we will get 3,000 meters. Then a point in the wing, which is the V sub 2, 70 meters per second, and calculate the pressure at this point. We'll find the P sub 2. So in order to find the P sub 1, we'll use the gradient region formula for pressure. We have 101325 Pascal times the 1 plus the lapse rate times the height times the standard sea level temperature raised to 5.26. Then we will arrive at the answer of P sub 1 is equals to 70,048.059 pascals. Then we'll use the gradient region for the density. Rho is equals to rho for the standard sea level 1.225 times the 1 plus lapse rate times 3,000 meters over the standard sea level of temperature 288.16 Kelvin raised to 4.26. Gradient region 3 kilometers. Then we'll use the Bernoulli's principle, or equation rather, and we'll arrange the formula. We'll get the P sub 2 the pressure at that point and plot the given values. We have P sub 1 plus 1 half density times the initial velocity minus 1 half density times the final velocity. Then our pressure at this point is 69457.859 Pascal. So Pascal is because kilogram over cubic meter times meter squared over second squared, then kilogram over meter times second squared is equivalent to Pascal. Sample problem 2. We consider the flow of air through a convergent divergent duct. The inlet, throat, and exit areas are 3, 1.5, and 2 meters squared. Respectively, the inlet and exit pressures are 1.02 times 10 raised to 5 Pascal and 1.1 times 10 raised to 5 Pascal. Newton over meter squared is Pascal. Calculate the flow velocity at the throat. Assume incompressible flow with standard sea level conditions. Standard sea level density. So we have the inlet of 3 meters squared, throat area of 1.5 meters squared, and the exit area of 2 meters squared. Then we have the inlet pressure of 1.02 times 10 raised to 5 Pascal and the exit pressure of 1 times 10 raised to 5 Pascal. Well, since assuming incompressible flow with standard sea level density, the density is 1.225 kilogram over cubic meter. We'll find the flow velocity at the throat, meaning V sub 1. First is we'll equate the conservation of mass to each other. A sub O, V sub O is equals to A sub 1, V sub 1 is equals to A sub 2, V sub 2. We'll need the V sub 1, so equate this formula, the equation rather, then we'll arrive at V sub O is equals to A sub 1 over A sub 0 times the V sub 1. This V sub 0, we will input this into the Bernoulli's equation later on to find the V sub 1. And the A sub 1, V sub 1 is equals to A sub 2, V sub 2. Rearrange again to find the V sub 1. So we can plot this V sub 2 into the Bernoulli's equation. So V sub 2 is equals to 3 over 4 V sub 1. Eliminate the unit since it's both meter squared. Then for the Bernoulli's equation, we rearrange this equation to find the throat velocity. Then we will arrive at this equation. V sub 1 is equals to the square root of 32 times the change in pressure over 5 times the rho or density. V sub 1 is equals to square root of 32 times 1.02 times 10 raised to 5 Pascal minus 1 times 10 raised to 5 Pascal over 5 times the density of 1.225 kilogram per cubic meter. So our answer will be velocity is equals to 102.220 meter per second. So that is the velocity in the throat section. So the cancellation of units, Newton over meter squared times the cubic meter over kilogram. So cross multiply since it's division, and we'll arrive at meter squared over second squared. Then square root will eliminate this, both the squared in the numerator and the denominator. So our final answer will be 102.220 meter per second. That's the inlet velocity. The throat velocity. Next is we'll solve the speed of sound. A Boeing 747 is cruising at a velocity of 250 meter per second at a standard altitude of 13 km. What is its Mach number? We have the velocity of 250 meter per second and the altitude of 13 km. So isothermal region 13 km, anything that is 11 km and up to 25 km is isothermal, meaning we have constant temperature of 216.66 Kelvin. So velocity is equals to 250 meter per second. Height is 13 kilometer isothermal. What is the Mach number? So like I said earlier, Mach number is the ratio of velocity over the speed of sound. So we'll compute for the speed of sound. So 250 of meter per second over the square root of gamma times the specific gas constant times the temperature in isothermal region. Then cancellation of units, Newton times meter over kilogram. We'll get meter squared over second squared, square root, eliminate the squared. Then we will eliminate the meter over second since Mach number is the ratio. Last problem is the high-speed missile is traveling at Mach number 3 at standard sea level. What is its velocity in miles per hour? So the Mach standard sea level, the temperature is 288.16 Kelvin. Mach number is 3 and we'll get the velocity in terms of miles per hour. Find the velocity since we have the Mach number, and we'll solve for the speed of sound. So V is equals to the Mach number times the square root of gamma times R times T. 3 times square root of 1.4 times the specific gas constant of 287.08 joules per kilogram times K. Eliminate K, then breakdown of unit, Newton over meter over kilogram. We will get the meter squared over second squared, square root, then we will get only the meter over second. So the velocity is 1020 times 1020.948 meter per second. And since we need the in terms of miles per hour, we'll convert the meter per second to miles per hour. Then the velocity is equals to 2284.284 miles per hour. So therefore, I conclude that incompressible flow is an idealization useful for low speed or subsonic aerodynamics, where the Mach number is low and change in density are negligible. As the flow velocity approach the speed of sound, the flow regime transition from subsonic to transonic and then supersonic and eventually hypersonic, and where compressibility effects become increasingly significant, requiring more complex analysis and consideration.